All right, so in my previous video, we walked through this example where we were computing the area bounded by these two polar curves. And if you remember towards the end of that video, I was telling myself, I feel like I'm forgetting something. I figured out what it was. When we found the area, we only found the area of this half of our region right here. I only found the area of that. So this is the area of half of my region. What I needed to do was then double this to get the area of the whole thing, because we have this symmetrical portion down here. So actually, the area that I want is this thing times 2, which would just make 3 times root 3 minus pi over 3. Okay, so I wanted to correct that before we moved on. Now that we've done that, let's go ahead and talk about arc length. So arc length is something we've already dealt with back in, well, we've done it a couple of times. We talked about it in chapter 8, and then we talked about it again in this chapter, chapter 10, specifically 10.2, and when we talked about parametric equations. What we're going to do here is think about our polar curves parametrically. And here's what I mean. Say you have a polar curve, again, given by r equals f of theta on some interval AB. Our goal is to find the length of that curve on this interval. But we can use our conversion formulas. We know that x is equal to r cosine of theta when we're converting to polar or rectangular from polar. But that r can now be replaced by an f of theta because this function sets these things equal to each other. So x is equal to f of theta cosine of theta. Similarly, y is equal to f of theta sine of theta. This is defining both x and y as functions of theta. So I'm going to think of theta as a parameter, like a t or something like that, from section 10.2, and that means I can use the results of 10.2 on this thing. So how do we go about finding arc length? Well, I know, I'm going to jump down here, this is what our arc length formula looks like from section 10.2 if our parameter is theta. It's the integral from a to b of the square root of the sum of the squares of dx d theta and dy d theta. So defining x and y the way that we did on the previous page, if I differentiate those, coming back here, notice x and y are both given as functions of theta, but more specifically products of functions of theta, f of theta times cosine, f of theta times sine. So evaluating the derivatives of those with respect to theta would involve using the product rule. Dx d theta becomes this. This is again from the product rule, dr d theta cosine of theta minus r sine of theta. And then if I apply to the product rule to my y equals f of theta sine of theta, I get this. Dr d theta equals sine of theta plus r cosine of theta. Now these r's would have looked like f of thetas in that derivation, but we can switch back and forth between r and f of theta because those are equal to each other. All right. Now what we're going to do is use a Pythagorean identity when trying to figure out what dx d theta squared plus dy d theta squared is. So dx d theta, which was this, if I square it, I'm squaring a binomial of sorts. And so I'm going to get a fairly large looking expression. It's going to have these 3 terms. You can verify this, but if you square this guy, you're going to end up with this guy here. If I square dy d theta, this one here, I end up with these 3 terms down here. Okay, that's just squaring them. Now, what we're going to look at is how to combine some like terms here. So for example, I have a couple of dr d theta squareds showing up, right? So if I were to add these together, I would have dr d theta squared plus cosine squared plus dr d theta squared sine squared. If I then factor the dr d theta squared out of that, what's left is cosine squared plus sine squared, which we know is 1. So that whole thing, when I combine these 2 terms, reduces to dr d theta squared. That's all that happens there. These 2 terms look identical except one is positive, one is negative. These cancel each other. And then here, when I add r squared plus sine squared plus r squared cosine squared, something similar happens where I can factor the r squared out and I have sine squared plus cosine squared, which is just 1, times the r squared that I had in the beginning, I get r squared there. So all of this junk simplifies to something much, much simpler looking. So what that tells me is that when I want to find the arc length of that curve, the dx d theta squared plus dy d theta squared under this radical can be swapped out for this. This is in polar. And this becomes my new arc length function, or arc length formula. Integral from a to b of the square root of r squared plus dr d theta squared d theta. Okay? Let's do an example where we have to compute the length of an arc of a given curve. So find the length of the curve r equals e to the power of theta over 2 from 0 to 2 pi over 2. Okay, so in order to do that, I needed r squared and I needed d theta dr, or dr d theta squared. Let's figure out what dr d theta is first. So that's very straightforward. It would just be 1/2 e to the theta over 2. Just differentiating that with respect to theta. Okay, so now I have r squared plus dr d theta squared, because that's what's going to appear under my radical in my arc length formula. Well, r squared is just e to the theta over 2 squared. And if I square that, the 2 in the denominator here is going to get canceled. I get e to the power of theta. Dr d theta squared, this guy, something very similar happens, but I also have to square the 1/2. So I get plus 1/4 e to the power of theta. This is 5/4 e to the power of theta. So now my arc length is found by taking the integral from 0 to pi over 2 in this case of the square root of this. Okay, d theta. Now I can take that fraction out. I'm going to get root 5 over 2, because I can take the square root of 4. That's 2. I get root 5 over 2. That comes out from 0 to pi over 2. And then the square root of e to the theta is just e to the theta over 2. Using rational exponents, it's easy to come up with that. This is pretty straightforward to integrate. I'm going to get root 5 e to the theta over 2. And we evaluate this from 0 to pi over 2. This would just be e equal to root 5 times, when I plug a pi over 2 into that, I get e to the pi over 4. When I plug a 0 into that, I get e to the 0, which is 1. That would be my arc length right there. All right, not bad, not bad. That's pretty straightforward. That's all we really want to talk about as far as arc length goes. We could do more examples, but you'll do that in the homework. Let's talk about tangents for the last application of this stuff. So my goal here is to figure out how to find the slope of tangent lines to a polar curve at various different points. And again, we're going to reuse some stuff that we found in section 10.2. We're going to think of x and y again as f of theta cosine of theta, f of theta sine of theta, where r equals f of theta is the curve that we're using this on. Okay, the benefit of this, as we saw before, is that x and y are being thought of parametrically, where theta is the parameter now. Okay, so when we dealt with tangents in 10.2, we discovered this. dy dx, which gives me the slope of tangent lines, is equal to dy d theta over dx d theta. Again, theta is my parameter here. But both dy d theta and dx d theta, we found those in the previous derivation over here. We've already computed dx d theta and dy d theta. Remember, we needed the product rule when we did that. So those become the numerator and denominator, okay? Now, this thing, I know it looks like a complicated formula, but this is what we would use when finding slopes of tangent lines to polar curves. This big quotient right here. And what we're going to do in one interesting case that occurs is if you want to find the slope of a tangent line to a polar curve at the pole specifically. So some of the polar curves that we've seen contained the pole, and to find a tangent to the pole specifically, the pole is the only point where r is equal to 0. So at the pole, these two terms would go away. R and R becomes 0, and I'm just left with dr d theta sine of theta over dr d theta cosine of theta. And as long as dr d theta is not equal to 0, we can cancel those out. And I just have sine of theta over cosine theta, or tangent of theta. So in this particular case, we have a much simpler formula where to find the slope of a tangent line at the pole is just tangent of theta, okay? So yeah, let's look at one example before we wrap things up. This is the type of problem you'll encounter in the homework. I want to find all points on the curve r equals 1 minus sine of theta where the tangent line is either horizontal or vertical. Going back here, I have this quotient which gives me the slope of tangent lines. Now, if my numerator is equal to 0 and my denominator is non-zero, then that would be an instance where this slope is equal to 0. That would be a horizontal tangent line. So horizontal tangent lines, or horizontal tangents, occur when that numerator, which looked like this, dr d theta, sine of theta, plus r cosine of theta is equal to 0, provided that this denominator is not also equal to 0. Okay, so we need to be careful with that. Similarly, if I want to find a vertical tangent, from Calculus 1, we saw that vertical tangents occur when we get a non-negative numerator in a quotient like this, but a 0 in our denominator. So vertical tangents will occur when this thing is equal to 0, as long as our numerator is not also equal to 0. So I'm going to say vertical tangents occur when that denominator looked like dr d theta cosine of theta minus r sine of theta equals 0. So we need to use this fact to answer this question. Okay, so I'm going to start computing some ingredients. Let's get dr d theta. That would just be negative cosine of theta. Okay, so now here, if I plug this in for the dr d theta, and then that r I'm going to represent as 1 minus sine of theta, I'm going to have this negative cosine of theta, that's the dr d theta, times sine of theta, plus r, which is really 1 minus sine of theta, times cosine of theta, equals 0. I want to solve this, okay? So if I distribute this cosine in, I'm going to get negative sine times cosine. I have another one of those right here. So that's going to give me negative 2 sine of theta cosine of theta. And then I'm going to get a plus cosine of theta right there, equals 0. Let's factor a cosine out. So cosine of theta times, then I can write this as 1 minus sine of theta, or 2 sine of theta, equals 0. This means that either cosine of theta equals 0 or 1 minus 2 sine of theta equals 0, which is equivalent to sine of theta equals 1/2. Okay? Where does this happen? Well, cosine is equal to 0 when theta is equal to pi over 2 or 3 pi over 2. Sine of theta occurs sine of theta equals 1/2 when theta is either equal to pi over 6 or 5 pi over 6. So here are 4 solutions that all give me a 0 in my numerator. Okay, we'll do something with that in a moment, but let's look at the denominator where we get vertical tangents from. So dr d theta times cosine. Dr d theta was negative cosine, so we have negative cosine of theta times cosine of theta. So that means I have negative cosine squared there. Minus r, which is 1 minus sine of theta times sine of theta equals 0. Or 0. That shouldn't be a theta, it's just 0. Okay, let's see if we can simplify this down. So this is like negative cosine squared of theta. Distributing the sine in here, I'm going to get negative 1 times sine, so negative sine of theta. And then I'm going to get negative times negative, which is positive, so plus sine squared of theta, and that is equal to 0. Okay? Now what I want to do is try to solve this. I think the easiest way to do this is to convert all of my cosines into sines, so I'm only dealing with one type of trig function. So cosine squared is 1 minus sine squared. Putting a negative in front of that flips that around. I get sine squared of theta minus 1. I have another sine squared right there, so let's call that 2 sine squared. And then I'm going to have this minus sine of theta here as well. Let me take that minus 1. I'm going to move that out. I'm going to have my sine of theta be there and my minus 1 be there. My reason for doing that is because now this looks like a quadratic. I can factor it. 2 sine of theta, this would be plus 1 times sine of theta minus 1 equals 0. This is how that would factor. This implies that sine of theta is either equal to negative 1/2, because that's what this would be if I set it equal to 0 and solve for sine, or sine of theta equals 1, which is if I set that guy equal to 0. So what values of theta do we get out of this? Well, sine of theta is equal to negative 1/2 at 5 pi over, 7 pi over 6, or 11 pi over 6. That's where that occurs. Grab my notes over here. Okay. Sine of theta is equal to 1 only at pi over 2. All right? So here's what I'm noticing. Because remember, these are the values of theta that are going to give us horizontal tangents, potentially. And these are the values of theta that are going to give us vertical tangents, potentially. And the reason I'm saying potentially is because these values of theta would cause my numerator to equal 0, and these would cause my denominator to equal 0, but we need them to not both be 0. So notice I have theta equals pi over 2 showing up in both lists. That means pi over 2 may or may not give us a horizontal or vertical tangent. It's kind of inconclusive. We'll address that in a second. But since I don't have any other repeats in any of these lists, everything except for these pi over 2's will give me the expected tangents. So horizontal tangents occur at which points? These are only the theta values for these points. I need to get the corresponding r's, but I can get that by plugging these thetas into this function right here. So for example, we're ignoring the pi over 2, but 3 pi over 2. Sine of 3 pi over 2 is negative 1, and 1 minus negative 1 is 2. So I get a horizontal tangent at 2, 3 pi over 2. Okay? Then pi over 6 and 5 pi over 6, both of these, when I plug them into sine, would give me 1/2. 1 minus 1/2 is 1/2. So I get a point 1/2 pi over 6 and 1/2 5 pi over 6. Both of those, 5 pi over 6. Both of those guys are going to give me horizontal tangents. Okay, now let's look at the vertical tangents. Okay, vertical tangents. Again, we're ignoring the pi over 2 here. I have 7 pi over 6 and 11 pi over 6. Plugging those into my function. At both 7 pi over 6, at both 7 pi over 6 and 11 pi over 6, sine of theta for either of those is equal to negative 1/2. And so r is equal to 1 minus negative 1/2, which is 3/2. So I get 3/2, 7 pi over 6, and 3/2, 11 pi over 6. Now I did say we would address the pi over 2, and I'm still going to do that, but I want to think about where these tangents would live if I actually graphed this thing. So what does the graph of this polar curve look like? Well, this I recognize as a cardioid. Okay, so I have 1 minus 1 sine of theta, 1 and 1. Remember, when those numbers are equal, we have a cardioid. And this one is oriented downwards because I have a negative sign there. So it's a cardioid that's going to look roughly like this. And no, I am not being very careful with my picture. It's just a rough idea. But from the picture, I can see 3 places where I am expecting to see horizontal tangents. Here, here, and here. And notice this would correspond to 3 pi over 2 down here. So 3 pi over 2, 2. These values here look like reflections across the polar axis, which would make sense if one of them was pi over 6, the other one would be 5 pi over 6, so that makes sense. Vertical tangents would occur around here. And notice that's corresponding to angles in the 3rd and 4th quadrants, which 7 pi over 6 and 11 pi over 6 would be, and they are reflections of each other across that vertical axis. So all of that makes sense. What is happening at pi over 2? Well, that is where, if you follow this cardioid from theta equals 0 to pi over 2, r shrinks down to 0 there. And you can confirm that if you plug pi over 2 in for your function. 1 minus 1 is 0. So we get that point at the pole. But these cardioids have like a cusp there. And we know from Calculus 1, when you have a cusp or a corner or something like that, there is no tangent line there. So that's the reason why we're not seeing a tangent line at pi over 2. That's why we're seeing that 0 over 0. It's neither a horizontal nor a vertical tangent. In fact, it doesn't have any tangent there at all. I could construct a kind of similar argument to that using limits. I'm not going to do that. We can just kind of resort to our intuition that we built up in Calculus 1 there. That's going to wrap up section 10.4 and the rest of chapter 10 that we cover in this class.